Rank. Good morning everyone. My name is NIRMALA, working as a degree maths lecturer in PV Siddhartha. Here I am going to explain the theorem, rank nullity theorem. Before going to explain the theorem, I discuss some definitions. First one is rank. Rank of a vector space, nullity of a linear transformation. Rank means it is a dimension of the R of T. R of T means it is a set containing all the images. Nullity means it is a set containing the elements whose images is equal to 0 bar. Nullity means dimension of n of t. Next, rank nullity theorem. U over f and v over f be two vector spaces. T from U to V is a linear transformation and U is a finite dimensional vector space. We have to prove that rank of t plus nullity of t is equal to dimension of U. Dimension of U. Prove that U over f, V over f be two vector spaces and T from U to V is a linear transformation. U is a finite dimensional vector space. Rank of T plus nullity of T is equal to dimension of T. Rank of T means dimension of R of T. Nullity of T means dimension of N of T. We know that N of T is equal to, it is a set containing all the elements whose images is equal to 0. Whose images is equal to 0. This is a whose images is equal to 0. We know that n of t is equal to alpha belongs to U, t of alpha is equal to 0. It is a null space. R of t, we know the definitions. Since n of t is a finite dimension vector space means every finite dimension vector space has a basis. So n of t has a basis. N of t contains all the elements which the images are is equal to 0. There exists a basis of n of t. Say this is equal to alpha 1, alpha 2 and so on alpha n. S is linearly independent because it is a basis, so it is linearly independent and L of S is equal to N of T and dimension of N of T is equal to M is equal to nullity. L of S is equal to dimension of N of T is equal to M because the basis of N of T is S. S contains elements, M number of elements. So the dimension of N of T is equal to M. Before S is a basis, so S is must be a subset of N of T. N of T is finite dimensional vector space of U, so N of T is subset of U also. S is linear subset of U. Then by basis extension theorem, S can be extended to form a basis of U. S is already a basis. By basis extension theorem, it can be extended to form a basis of U. Okay, S can be extended to form a basis, that is P. P contains alpha 1, alpha 2 and so on alpha n, beta 1, beta 2 and so on beta. P is a basis for U. P is linearly independent because P is extended basis. Basis conditions, P is linearly independent and L of P is equal to M plus N. L of P is equal to U. So dimension of U is equal to how many number of elements in P? M plus N. So dimension of U is equal to M plus N. Next, consider Q. Q is equal to T beta 1, comma T beta 2 and so on T beta. Clearly Q is subset of R of T. Now we show that Q is the basis of range of T. Range of T. Q is the basis of range of T. We show that Q is linearly independent and L of Q is equal to R of T. We show that Q is linearly independent. Linearly independent means we have to write the linear combination and all the constants is equal to 0. Then we say that the elements are linearly independent. B1 T beta 1 plus B2 T beta 2 plus and so on T and T beta n is equal to 0. We have we have to write by the outside T. T B1 beta 1 plus T B2 beta 2 plus and so on T Bn beta n is equal to 0. T of A alpha plus B beta. A into T alpha plus B into T beta. It is also written as T of A alpha plus B beta. Here we are using the condition because linear transformation is a linear transformation, that's why we are using this condition. N of T is also linear transformation. These all are the elements of N of T, so N of T is linear transformation condition we are used. Here beta 1 T of beta 1 plus beta 2 B2 beta 2 plus and so on Bn beta n is equal to 0. T of alpha is equal to 0. That means alpha belongs to N of T. Here in place of alpha, here we have b1 beta 1 plus b2 beta 2 plus and so on. Bn beta n belongs to n. Okay, n of t is already equal to L of s. So b1 beta 1 plus b2 beta 2 plus and so on. Bn beta n belongs to L of s. Okay, L of s is equal to n of t. By definition of L of s, a1 alpha 1 plus a2 alpha 2 plus and so on. am alpha. Come to b1 beta 1, we come to right hand side. This is a linear combination of the elements of p. We know that p is already linearly independent. Linearly independent means all the constants is equal to 0. Constants means a's and b's all are equal to 0. Okay, here all the scalars in the above linear combination are equal to 0. Means a1 a2 is equal to a1 is equal to a2 is equal to and so on. am is equal to b1 is equal to b2 is equal to and so on. bn is equal to 0. Okay, next the existed scalars in 1 all are 0. So q is equal to t beta 1 comma t beta 2 comma and so on. t beta 1 is linearly independent because the linear combination of all t beta 1 t beta 2 and so on t beta 1 all constants is equal to 0. So that's why the elements are linearly independent. The elements are all are belongs to q. So q is linearly independent. Now we have to show that L of q is equal to R of t. Since q is subset of R of t, it is nothing but there is nothing to prove. Q is subset of R of t. That implies L of q is subset of R of t. Subset of R of t. We have to show that R of t is subset of L of t. We have to take an element from R of t. That is gamma. All elements in R of t are images. So gamma is equal to some t alpha. Okay. Next, since alpha belongs to u, that implies alpha belongs to u. Alpha belongs to u. U is equal to L of p. So alpha is equal to linear combination of elements of p. We have to write what are the elements in p? Alphas and betas. So we have to write the linear combination. a1 alpha 1 plus a2 alpha 2 plus and so on. am alpha m plus b1 beta 1 plus b2 beta 2 plus and so on. bn beta n. Gamma is equal to t alpha. We have applying t on both sides. Gamma is equal to t of alpha is equal to t of alpha. We know that gamma. So gamma is equal to t of alpha is equal to t of a1 alpha 1 plus a2 alpha 2 plus and so on. am alpha m plus b1 beta 1 plus b2 beta 2 plus and so on. bn beta n. Okay, we have applying t individual terms. Applying t to individual terms. Here also we have linear transformation definition. Here applying. Here applying. a1 t alpha 1 plus a2 t alpha 2 plus and so on. am t alpha m. b1 t beta 1 beta 1 plus b2 t beta 2 plus and so on. bm t beta n. Okay, here t alpha 1 t alpha 2 here this all are elements is equal to 0 because all images is equal to 0 plus b1 t beta 1 plus beta 2 plus and so on t beta n. These are all the elements of q belongs to linear combination of q. So gamma belongs to R of t. Gamma belongs to L of q. So R of t is subset of L of q. From t and t we have to L of q is equal to R of t. Dimension of R of t is equal to n rank of t. It is equal to gamma of t. Dimension of u is equal to m plus n. Nullity of t plus rank of t. Rank of t plus nullity of t is equal to dimension of q. Okay, gamma of t plus rho of t is equal to dimension of u. R dimension of R of t plus dimension of n of t is equal to dimension of u is equal to m plus n. Here dimension of R of t and gamma of t, rank of t. These are the three common terms. These three are single terms. Rank of t and dimension of R of t, gamma of t. These are the single terms. Nullity and rho of t, dimension of n of t. These three are the singular terms. Okay, this three words are same. We have to use anywhere. Okay, particularly we have to memorize what is dimension. Dimension is nothing but it is the number of elements in basis of that vector space. Okay, the number of elements in basis is the dimension of that set. Okay, thank you.